Hello students, today's lecture is on limit state method. Here we'll understand the concept of singly reinforced section. So when I'm saying singly reinforced section, obviously we'll try to understand what is doubly reinforced section. Under singly and doubly we have also T sections as well as EL sections. So let us start with this method, singly reinforced section. Now first we'll try to understand the design philosophies. Already you have learned there are three design philosophies. First one is working stress method, second one is ultimate load method, and third one is limit state method. Now, limit state method, it is the combination of first two methods, that is working stress method and ultimate load method. That means whatever the positive points are there, good points are, these are the combined, and we got new method, that is limit state method. So exactly what is this limit state method? So it is the condition, or we can say it's the state at which structure becomes unfit for its intended use. It is called as limit state. This is considered as just like a boundary. Okay, for anything you have to fix the boundary beyond which if some value exceeds, then you can say that it is unsafe. Okay, that is simply limit state. So in other words, we can say limit state are the acceptable limits for the safety and serviceability requirements. Not only safety and serviceability, but also durability. Okay, so these are the three different limit states. Okay, so we'll see the three major types of the limit state. First one is limit state of collapse, second one is limit state of serviceability, and third one is limit state of durability. Okay, so when we say limit state of collapse, okay, that means we talk about ultimate state, that is ultimate load method. Okay, already you understood that. Now at ultimate condition, what will happen? That part we are considering at limit state of collapse. Okay, limit state of serviceability means exactly during the working condition or during the service conditions. Okay, whatever is the performance of the structure, okay, that we'll see under limit state of serviceability. And third one is limit state of durability. It is nothing but the response of the material subjected to aggressive environmental condition. Okay, obviously all three gives us different limit states. Okay, so one by one we'll see in detail. So first one is limit state of collapse. Okay, so it deals with the strength and stability of the structure subjected to maximum design loads out of the possible combinations of several types of loads. Okay, now the structure may subjected to dead load, live load, wind load, snow load, as well as earthquake load. Okay, in IS code different combinations are given. Okay, along with safety factors. Okay, the load factors are given. Okay, so whatever the critical load combination will be there, which gives maximum bending moments, maximum shear force. Okay, so for that you have to check strength and stability of the structure. That means at that condition, at ultimate condition, okay, your structure must be safe. This is a limit state of collapse. So therefore this limit state ensures that neither any part nor the whole structure, okay, should collapse or become unstable under any combination of expected overloads. Well, so this is limit state of collapse. Okay, as I told you, we talk here about the ultimate condition. Now, the second one is limit state of serviceability. As I told you, the serviceability is related to satisfactory performance of the structure during working condition or service condition. Working condition or service condition means actual when the structure is subjected to the loads for which we are designed. Okay, normally when we consider, suppose a classroom is there, and in that classroom the capacity of the classroom is 60 students. Okay, so the load of the 60 students will be considered as working condition. Okay, when you multiply it by a suitable factor of safety, let's say 1.5, so the 60 will become 90. So that 90 is at ultimate condition. Okay, so this is working condition. That means when 60 students are there in the classroom, we'll consider that load class as a service condition or working condition. Now limit state talks about this condition. Okay, so this limit state of serviceability again can be divided into two types. Okay, the first one is limit state of deflection and second one is limit state of cracking. Now deflection. Okay, deflection, that means when there is a because of transverse load, okay, the beam may get deflected, it may bend. Okay, so this excessive deflection creates many problems. For example, cracking of the walls, maybe partitions or also the furniture. Then cracking of ceiling finishes. If deflection is there, obviously the cracks will occur, the crack will occur. So whatever the ceiling finish will provide, that will also collapse. Okay? It spoils the appearance of the structure. Not only that, because of sagging, the ponding on the roofs will take place, and also the most important is we may have feeling of lack of safety. So these are the problems related to deflection. So we don't want deflection. Then how to take care of deflection? So as per IS 456, certain clauses are given to control the deflection. These are called as deflection checks. L by T ratios are given. Okay, like 20, 26, 7. 7 is for cantilever, 20 is for simply supported, and 26 is for continuous. Okay. So these limit states, these L by T ratios are given, which ensures the limit state for deflection. Then second one is limit state of cracking. So there are also some problems associated with cracking. Okay, for example, leakage. If leakage is there, obviously the corrosion of the bars will take place. Okay, if corrosion will take place, then the continuous longitudinal cracks will develop. Okay, and the structure will lose its strength. So also reduction in the stiffness of the member because of cracks. Okay, it will also spoil the appearance of the structure, and again it gives the feeling of lack of safety. So these are the problems associated with the cracking. Now, how to ensure this limit state of cracking? So in IS code, again, the control is given on crack width. Okay, so the strain in the concrete is restricted to 0.0035. Okay, normally when we design beam under flexure, we design it as a crack member. Okay, well, but the limits are given for the crack width. The checks are given in IS code against the crack width. Then third limit state, that is limit state of durability. So durability is related to the durability of the structure against the action of aggressive environmental conditions. Which are the aggressive environmental conditions? Like when the structure is subjected to fire, rain, okay, percolation of water through the members, then the effect of weathering, okay, like temperature change, some chemical change, okay, or chemical attack. So the resistance of the material to these aggressive environmental conditions, that is called as durability. Okay. So again, this limit state of durability can be divided into three types. Okay, that is first one is limit state of fire resistance. How will you ensure? So in IS code, one table is given. In that table, cover, nominal cover to be provided against fire resistance. Like if you want to hold fire for half an hour or 1 hour or 2 hours, accordingly the covers are given. Okay, so I have to ensure the required cover, okay, according to the fire resistance. Then second one is limit state of environmental and chemical actions. So for this also the tables are given to control the quantities of different hazardous chemicals, okay, in the concrete. Okay, so the controls are given. So accordingly you have to control these. These chemicals may get introduced through the aggregates or the cement or the water. Okay, or even admixtures also. The limit state of resistance to accidental or catastrophic collapse. Okay. Obviously, now accidental or catastrophic collapse, for that we cannot have some loads. Okay, obviously, but so factors what we consider. Okay, in those factors, obviously this part can be considered. So these are the three limit states. Let's move to next part. Now, two important concepts are given by IS code. The first one is characteristic strength and second one is characteristic load. Now this characteristic strength and characteristic load, these two concepts are based on probability. Okay. Now what is this concept? So characteristic strength, the term characteristic strength means that value of the strength of the material below which not more than 5% of the test results are expected to fall. In simple language, the success ratio is more than 95%. Okay, or you can say the characteristic strength has 95% reliability. Okay, for example, if we are testing 100 cubes, okay, let's say the size of the cube is 150 by 150 by 150, okay, and we have grade of concrete M20. Okay, well, we can say this 20 Newton per mm square as characteristic strength only when more than 95 cubes gives you values equal to or more than 20 Newton per mm square. Okay, so probability of failure is less than 5%. That means maximum 5 cubes can give results less than 20. Then and then only we can say 20 Newton per mm square is the characteristic strength. Okay. Similarly, another definition is characteristic load. Okay. Now, when we consider characteristic load, it means it is that value of load which has again 95% probability of not being exceeded during the life of the structure. Okay, so you have to take such a value, okay, of live load, or which is called as imposed load. Okay, so when I have to ensure that during the entire lifespan of the structure, the load will not exceed the value which were considered during the design. Okay, and that probability is almost 95% or more than 95%. Okay, so only 5% chances are there the load may get exceeded more than the design load. Okay, so characteristic strength and characteristic load. Okay, for this both the concepts, IS code gives different values of factors. Okay, we can say safety factors. Okay, so in the next slide we'll see the safety factors. Okay, now these factors are called as partial safety factors. So we'll also see the reason why these are called as partial safety factors. Okay, not only safety factors. Okay, well, so here is the reason. Now, the safety of the structure depends on two principal design factors. Okay, one is the material strength and second one load. Okay, that means when we consider material strength, then that means we have to consider the actual property of the material. Okay, now if you consider RCC, so obviously steel and concrete, both the materials you have to consider. Okay, and loads, when you consider loads, obviously dead load, live load, wind load, earthquake. Okay, these are different types of loads which you have to consider. Okay, but problem is that both material strength and loads, these are not functions of each other. That means if you apply load factor for one entity, okay, it automatically it will not get applied to the other quantity, okay, or entity. So obviously you have to apply different safety factors, and hence the name partial safety factors. Okay, so the first factor will apply for material strength and second factor will apply for load. Okay, and partially these two factors contribute for the safety, and hence these factors are referred as partial safety factors. Okay, so we'll see first factor, that is design strength of material. Okay, now when we say design strength of material, let's say it is denoted by F suffix D. So Fd is equal to Fk divided by gamma m. Now Fk, it is the characteristic strength. Okay, so we are talking about material property, and gamma m, it is the partial safety factor for material. Well, now when characteristic strength is divided by gamma m, that gives you design strength. Fine. Now there are two different values which are given by IS code. Okay, first value is 1.15, that is for steel, and second value is 1.5, it is for concrete. Now again the question is why the value for partial safety factor is higher for concrete and for steel it is less. Since steel is manufactured in the industry, there is perfect control on the manufacturing process. Okay, so quality can be maintained in the steel, and hence factor of safety for steel is lower. Whereas concrete, though make design is carried out in the laboratory, but actual casting is to be done in the on the site or in the RMC plants. Okay, so there are many factors, okay, which affects the strength of concrete. Okay, and there are some factors which are many times beyond control also. Okay, so obviously variation is more in case of concrete, and hence higher factor of safety is considered for concrete as compared to steel. Now second factor of safety, it is for load. So for load, if you say design load is given by Fd, okay, so we'll consider characteristic load multiplied by gamma f. So gamma f is the safety factor for load. Okay, so it is the multiplying factor. Earlier we saw gamma m, that was the dividing factor. Now this is the multiplying factor. Okay, well, IS 456 gives a table for this load factor. Okay, so again different factors are given for limit state of collapse, okay, and different factors are given for limit state of serviceability. Okay, so here in the table, column number 2, 3 and 4, this gives us the load factor for limit state of collapse, and remaining 3 column gives us load factor for limit state of serviceability. Now here some combinations are given. Okay, let's say first row, it is the dead load plus imposed load. Now dead load plus imposed load, it is the first load combination in which load factor is 1.5. Okay, for both, and at working condition or serviceability condition it is 1 only. Okay. Well, when we consider dead load plus wind load, okay, so in that 1.5 must be multiplied by the dead load and 0.9 is to be multiplied by wind load. Okay, and when you consider three loads like dead load plus imposed load plus wind load, okay, then multiplication factor, that means load factor, is 1.2, okay, for each load. Okay, well, now when we consider earthquake load, so wind load is to be replaced by earthquake load. Okay, so if you calculate, you will find that at limit state of collapse there will be total 13 combinations for wind load if we design it for wind load. Okay, and if we design it for earthquake load, again we have 13 load combinations, but in both the combinations, okay, the first combination, that is 1.5 dead load plus live load, is common. Okay, hence 13 plus 12, total 25 load combinations if you are designing for wind load as well as earthquake load. Okay, well, so this is limit state of collapse. Okay, a similar type of combinations we can have for limit state of serviceability also. But when we design, okay, normally when design for limit state of collapse, okay, so obviously you have to consider 25 load combinations. But when you check the member for deflection, you need to consider the load factors for limit state of serviceability. Okay, so remember, two different factors are to be used at two different design steps. Okay, now we'll move to the next part. Okay, that is properties of concrete. Now, here in this diagram, three different curves are given. Okay, so what are these three different curves? Okay, that we'll see one by one. Okay, well, so let me consider this first curve. We choose a paint color. Okay. Now, see, this is the first curve. Okay, is the parabolic curve. Okay, normally this curve is like this. Okay, when you consider, actually test the concrete cube, but this is the idealized curve. Okay, so from the ultimate value a straight line is considered. Okay, and we'll call this as FCK. Fine. What is FCK? It is characteristic compressive strength of concrete. Okay, that means when you test a cube of 150 by 150 by 150 size, okay, after 28 days of curing, okay, what is the strength we get? Okay, that is the FCK. As I told you, you have to test number of cubes and then you have to decide, okay, what is the characteristic strength of that concrete. Okay, well, now this is the actual stress strain curve. Okay, with little bit modification. Now this FCK is multiplied here by 0.67 FCK. Now, why this? What is this value 0.67? Okay, please remember, this FCK is the value given by concrete of mold. Okay, which is the steel mold, proper cast iron steel mold, compacted very properly. Okay, but and size is only 150 by 150 by 150. But when you see the concrete of actual member, okay, it may be a column or it may be a beam. Okay, the sizes are quite larger than the cube, like 230 by 380 or 300 by 600 or 300 by 750. Okay, that too again, always we never use the steel formwork. Okay, normally we use wooden formwork. Okay, so obviously whatever the compaction, the quality of compaction we get in case of concrete cube, the same quality is not possible for the concrete of the concrete member. Okay, well, now in that case the strength will decrease. Okay, and this change or decrease in strain is considered as 33%. Okay, and hence this factor 0.67 FCK. Okay, this factor is considered as 0.67 FCK. Now this 0.67 FCK is divided by gamma m. Now what is gamma m? Earlier in the earlier slide we saw it is the safety factor, partial safety factor for material. Okay, so gamma m value for concrete it is 1.5. Okay, it is for 1.5. When you substitute this value gamma m 1.5, okay, so this 0.67 divided by 1.5, okay, now we have the value 0.446 FCK. Okay, so in the design for flexure we consider this third curve, okay, which is having value here 0.446 FCK. Okay, now got the difference, how to get the value from FCK to 0.446 FCK here. Okay, yes, now all these horizontal values we saw, but what about the vertical values? Okay, so here 0.002, that is the strain. Okay, and this strain, so first strain we consider as linear and non-linear part here. Okay, particularly it is related to steel. Okay, but in concrete also the similar values are considered. Okay, well, so here up to 0.002 the curves are considered, and then the straight lines are extended up to 0.0035. So maximum strain value is considered as 0.0035. Okay, now these are the design curves, design stress strain curve for concrete. Okay, now let's move to steel. Now particularly in general there are two types of the steel. First one is mild steel and second one is HYSD, that is high yield strength deformed bars. Okay, when you consider mild steel you will find in case of mild steel the yield point is very definite, a fixed point. Okay, see now in this case this is the point, okay, where you will find there is a change in the slope of the stress strain curve. Okay, and this fixed point, okay, that is called as yield point. Okay, yeah, in actual stress strain curve you will find there is upper yield point, lower yield point. Okay, but normally we consider the lower yield point. Okay, this is the lower yield point. Okay, and this value is about 250 Newton per mm square, and hence the steel is called as Fe 250. Okay, here I written, okay, Fe 250 is the steel. Okay, well, the slope of this line, this is called as Young's modulus, and it is considered as 2 into 10 raised to 5 Newton per mm square. Okay. Well, now as we saw that in case of steel, the material safety factor is 1.15. So here this Fy is divided by 1.15. Okay, and we got here 217 Newton per mm square. Okay, so this is the strength of the steel which is to be considered while designing. Right? Now we'll see another type of the steel, and that is called as HYSD steel. Okay. Now in case of HYSD steel, problem is there is no fixed yield point. Okay. See, this is a curvature. It's a continuous curvature. Okay. Well, actual curve is little bit different. Actual curve you will find, okay, something like this, and then you have the breaking point. Okay, so we are just considering the part of that. Okay, well, in high school it is given up to what value you have to consider that. Okay, well, now in this case, this Fy is divided by again the partial safety factor for material 1.15. Okay, and we get here 0.87 Fy. So finally the value which we will consider is 0.87 Fy. Okay, but as I told you that there is no fixed yield point here. Okay, then how to consider the yield point or the stress, okay, which is to be considered. Okay, well, so one procedure you have to follow. You have to draw a line parallel to initial curvature, okay, from 0.2% strain. Okay, 0.2% means 0.002. Okay, so well, here this is the value 0.002. So 0.2% strain. This is the dotted line which is parallel to initial curvature. Okay, this line cuts the stress strain curve at the point. Okay, and that stress is called as 0.2% proof stress. Okay, so when we say it's a Fe415, so Fe415 means this value. Okay, that means this dotted line cuts the curve at 415 Newton per mm square. Okay, well, so that is 0.2% proof stress. So if the steel is 415, that value is 415 Newton per mm square. If the steel is 500, we get that value as 500 Newton per mm square, and for 550 we get here 550 Newton per mm square. So when we say Fe415 or 500 or 550, these values, the numeric values, are nothing but 0.2% proof stress. Okay, and the procedure which I told you to determine this 0.2% proof stress. Yeah, but in HYSD case, steel bars also E value is considered as 2 into 10 raised to 5. Remember. Now we'll see the assumptions for limit state of collapse in flexure. Now the basic assumptions involved are given by IS 456 in clause 38.1. Okay. So what's the first assumption? First assumption is plane sections normal to the beam axis remain plane after bending. Now what is the importance of this assumption? The importance of this assumption is that strain diagram is linear. That means strain varies linearly with the distance from the neutral axis. Okay. So strain is proportional to the distance from the neutral axis, okay, that is the linearity of the strain is ensured because of this first assumption. The second assumption is the maximum compressive strain in concrete, that means at the outermost fiber, okay, shall be taken as 0.0035. Already we saw this in the stress strain curve, okay. Well, the notation used here is epsilon cu. Well, then the third assumption, already we saw this, okay, earlier. What is that? Is the relationship between the compressive stress distribution in concrete, okay, and the strain in concrete. So that relationship, okay, stress versus strain, okay, obviously when we consider across the cross section, that relationship can be assumed to be rectangular or trapezoidal or parabolic, okay, or any suitable shape. So in IS code, the parabolic shape is given, okay, the upper part is rectangular and the lower part is parabolic, okay. Such type of stress block diagram is given by IS code with the top width as 0.446 FCK, okay. And how do we get that 0.446 FCK? In the next line it is given, okay. For the design purpose, the compressive strength of concrete in the structure shall be assumed to be 0.67 times, okay. So already we saw this is the 0.67 times. It is nothing but it is the strength of concrete in the concrete member, like beam or column or slab, okay. Well, and then it is divided by factor of safety 1.5, and that's how we get 0.446 FCK, that is the top width of that stress block. Next assumption is the tensile strength of concrete is ignored, though in IS code it is given that tensile strength of concrete can be considered as 0.7 under root of FCK, okay, but normally it is ignored while designing. Well, then the stresses in the reinforcement are derived from the representative stress strain curve. Already we saw the stress strain curves, okay. For the design purpose, the partial safety factor equal to 1.15 is to be used, okay, and that's how we get 0.87 Fi as the value of the design stress, okay. And the maximum strain in the tension reinforcement in the section at failure shall not be less than Fi divided by 1.15 Es plus 0.002, okay. Well, now this first part is the linear part and the second part is non-linear part, okay. So I'm saying this is the first part, okay, of this equation. This is the linear, okay, and this is the non-linear part of the stress strain curve, okay. Now next slide, it is related to types of reinforced concrete beams, okay. Well, now as I told you, normally the beam can be designed as a rectangular section or flame section, okay. Same, rectangular section is again of two types, singly reinforced and doubly reinforced, okay. So first we'll see what is singly reinforced section and doubly reinforced section, then we'll go to singly reinforced flame section, okay. Well, now flame section means what? When a slab is constructed along with beam. Suppose the beam is exactly at the center, okay, and this is the slab, something like this, okay. See the cross section, it looks like T, okay, and hence it is called as T section. If the beam is at one end, okay, it's look like L, inverted L, and it is called as L beam, okay. Well, the portion of the slab can be considered along with the beam portion, and hence the name flame section, okay. But always you cannot design it as a flame section, okay. There are some exceptions, okay. We'll see this on the next slide, okay. First we'll see here singly and doubly reinforced section, okay. See the diagram, okay. Well, these diagrams are taken from the notes of IIT Kharagpur, okay. Thanks to them, very beautiful diagrams are created. Well, now here in the first diagram you will see the three bars are shown here, okay, as a representative three bars, okay, and their title is given as this is the tension reinforcement, okay, the steel bars in tension, okay, and two bars are shown here, okay. These are hanger bars, are also called as anchor bars, since a stirrup is to be provided, okay, and to keep the stirrup or to have the proper shape of the beam, okay. Well, normally minimum two bars are provided at top, okay, which also holds the stirrups in position, okay, and the bottom steel is the main steel, okay. So here steel is provided at tension phase, okay, and hence it is called as singly reinforced section, okay. That means steel is provided at one phase only, hence called as singly reinforced section, okay. Well, now another diagram. In this first diagram, steel is provided at bottom, and the second diagram, steel is provided at top, okay. Well, normally what happens at midspan, we get sagging bending moment. For sagging bending moment, we have tension at bottom and compression at top. Okay, and hence to take care of the tension which is at bottom, it is necessary to provide tension steel at bottom. Okay, opposite to that, at support, negative bending moment occurs. That means hogging bending moment occurs, in which tension occurs at top and compression occurs at bottom. Okay, and hence main reinforcement is provided at top. Okay, so what's the definition of singly reinforced section? You cannot say always at top or always at bottom. Okay, when steel is provided only at one face, and that is also a tension face, it is called as singly reinforced section. Okay, well, the next slide that we'll see related to double reinforced section. Now in this slide, double reinforced section, see in the first diagram, the steel is provided at bottom also and at top also. Okay, now here these are not called as hanger bars or anchor bars. Okay, now tension steel along is provided at bottom, compression steel is provided at top, and vice versa. Okay, in the another diagram, okay, compression steel is provided at bottom and tension steel is provided at top. Okay, it means at both the faces steel is provided. Okay, such type of beams are called as double reinforced section. Okay, why do you need such type of beams? Okay, so there are some requirements, okay, or certain conditions when you cannot increase depth of the beam. Okay, so when your dimensions are restricted, okay, at that time we need to provide double reinforced section. Okay, that means we provide additional steel on the compression side that reduces depth of the beam. Okay, so in detail we'll see this while dealing with double reinforced section. Okay, right now we'll try to understand the difference between singly and double reinforced beam. Okay, now in the first diagram, when we have sagging bending moment, okay, and the second diagram when we have hogging bending moment. Okay, now next slide is related to flange section. Okay, particularly again there are two types, T beam and L beam. Okay, well, now this flange, that means the part of the slab, okay, it is in compression side. Okay, and the top portion of the beam is also under compression. Okay, and hence we can take the benefit of the concrete flange section, which is the large concrete area, okay, which resists compression. Okay, and obviously we get very economical beam section. That means the concrete also get reduced and also the steel get reduced, because obviously the concrete is provided for the slab. Okay, and overall depth of the beam get reduced and also the requirement of the steel also get reduced. Okay, well, here so tension steel is provided at bottom and at top anchor bars are provided. So this is singly reinforced T beam, okay, at midspan section. Okay, well, now this is singly reinforced T beam under sorry, this is not singly reinforced, this is doubly reinforced. Okay, sorry for this. Okay, it is doubly reinforced T beam. Okay, well, now doubly reinforced T beam, in that tension is at bottom and compression is at top. Okay, that means T beam can be designed as singly as well as doubly reinforced section. Now always you cannot take the benefit of that flange. Okay, so for this example, okay, now this is the beam where tension is at top. See, tension reinforcement is provided at top. Okay, and anchor bars are provided at bottom. So flange is at tension phase, but concrete flange cannot take tension. So obviously you cannot consider contribution of the concrete flange. Hence, though it looks like T beam, but you cannot design this as T beam. You have to design it as rectangular beam only. Okay, and hence already I had written here. Okay, singly reinforced T beam under hogging bending moment. Okay, hogging is negative bending moment. Okay, so it is to be designed as rectangular section. Fine. Well, now in this case, again tension is at top. Okay, and compression reinforcement is at bottom. Okay, so here also flange is at top. Okay, though the beam is doubly reinforced, but again you cannot consider the contribution of the flange. Okay, and hence this beam is also to be designed as rectangular beam. Next one is when slab is available on one side only. Okay, then it is called as L beam. Okay, so again the similar concept we can adopt that which we have adopted for T beam. Okay, like singly reinforced L beam under sagging bending moment. Okay, so main steel is provided at bottom and anchor bars are provided at top. So this is singly reinforced L beam. Okay, similarly we have doubly reinforced L beam. Okay, so main steel is provided, that means tension steel is provided at bottom and compression steel is provided at top. Now just like T beam, here also when the tension is at the top face and flange is also at the top face, you cannot consider contribution of the flange, okay, because flange cannot contribute while resisting the tension, okay, it contributes only while resisting compression, okay. So obviously here also, though it looks like L beam, but you have to design it as rectangular beam, okay. In case of doubly reinforced L beam, again the problem is the similar one, okay, because the tension is at top and flange is also at top, so you cannot consider contribution of the flange. Hence, this beam is also designed as the rectangular beam. Okay, well, so that's it for today. Okay, we'll stop here. In the next lecture, we'll start with the properties of singly reinforced section. Okay, thank you.